Alrighty, hello everyone. Today we're looking at section 1.4, which is all about shifting, reflecting, and stretching graphs. So what we're really looking at here is a quick little review of Algebra 2, right? So our three objectives for today are, by the end of this lesson, I will be able to recognize the graph of parent functions, right? What does the original graph of that parent function look like? We're going to use vertical and horizontal shifts and reflections to to graph functions. And then we're going to use non-rigid transformations to graph functions. So that one might be a little bit new. We did talk about it a little bit in Algebra 2, but not as much. So um, the first two should look at least familiar, even if you don't remember. And then this last one we'll just have to go over again. Okay, so using a graphing calculator here, okay, we want to compare the graphs of f of x equals x squared and g of x equals x squared minus 3. And the question is, what happens? I'll actually see if I can scroll down a little bit more. The question is, what happens when a number is subtracted from the function? So hopefully we remember, right? And if you want to graph this on your graphing calculator, go ahead, pause the video and look at it. But hopefully we remember that when we add or subtract a number outside, so in this case, when we subtract a number outside of the parent function, it shifts the graph down. So what happens when a number is subtracted from a function? The graph shifts down. So nice and easy. So I have x squared, which is my parabola, right? And then x squared minus 3 just moves down 3 units. What about the graphs of absolute value of x and absolute value of x plus 4? What does this plus 4 do, right? What happens when a number is added to the function? So exactly what you think, the graph shifts up. Shifts up. Right, so absolute value is that perfect V, okay? And so then all we're doing is moving it up 4 units. The next one, compare the graphs of square root of x and square root of x plus 6. Notice the plus 6 here is inside the function, right? It's inside the square root. So what happens when a number is added to x inside the function? And this is when we have to remember that we go the opposite direction of what we think, right? So here the graph shifts. The question is, does it shift left or does it shift right? Well, here's a super easy way to remember, is it's just always the opposite sign, right? So positive 6 seems like it would go to the right, but it's actually to the left. And the reason for that is, if I were to set what's inside the function, which in this case is x plus 6, if I were to set that equal to 0 and solve, I would get that x is actually at the coordinate of negative 6. So that's to the left. Okay. Same thing here. What happens when a number is subtracted from x inside a function? Right, so I have x minus 3. Same thing, I could do it this way, or I could just do it like this, but in my head, right? Set what's inside the function equal to 0. So I get x is positive 3, which is to the right. So this graph shifts right. Right, that graph goes to the right. So again, you're more than welcome to mess around with your graphing calculator there and figure those out. But I figured it was faster to just talk about them, right? Okay, so here we go. Last part of this problem. compare the graphs of x cubed and x plus 3 cubed plus 2. Is x plus 3 cubed plus 2 shifted 3 units to the right and 2 units up? Question mark. So let's look. This plus 3, because it's inside the function, shifts it actually to the left. So no, this does not work, right? No, it's shifted 3 units to the left, 3 units left, and 2 units up. So the up part they were right about, but they said that it was going to the right, but it's actually going to the left. Again, if I set x plus 3 equals 0, I get x is equal to negative 3. And you don't have to do this part, or you could do this part in your head, but just to show you why we're getting those answers. Okay, example 2. The graph of f of x equals x squared is shown in the first figure. So this is the parent graph. So this is the parent graph. I guess it's called f of x up above, isn't it? Do it right. F of x equals x squared. Okay, write an equation for the other two functions. So here, the question is, has the graph moved left or right? And the answer is no. So I'm going to call this one g of x. Since the graph has not moved left or right, I don't have anything within that x squared. It's not going to be x plus 4 squared. It's not going to be x minus 6 squared, stuff like that. Okay? The only thing I have done, though, is I have raised this up vertically. So since it's vertically, it's going to be outside the function, and it's just plus 4. Okay? Over here, looks like I've moved it to the left, too. So I'm going to call this one h of x. Since I've moved it to the left 2, this is going to be x plus 2 inside the parentheses. And then I've also moved it down 1, so it'll be minus 1. All good? Feeling good? Feeling great? Y'all know what's going on? Reach out if you are struggling on this in any way, okay? So now we're going to kind of practice going the other way. First thing to notice, at least for part A, is that the parent graph is x squared. Okay, so I know that the parent graph is x squared. And I should know, because we took algebra 2 and we all passed algebra 2, that the parent graph of x squared, right, is 0, 0, 1, 1, 2, 4, 3, 9, and negative 1, 1, negative 2, 4, 3, 9. So those are my quote-unquote parent graph points. Okay, so what we're going to do now is look at my equation. So this tells me that I go to the right 2, right? Because it's x minus 2, so it's to the right 2. And then the minus 3 tells me that I go down 3. So every single one of these points, here's 0, 0, I'm going to go right 2, down 3. And then draw my point. 1, 1, right 2, down 1, 2, 3. Right 2, down 1, 2, 3. Right 2, 1, 2, 3. And then again over here. Boom. Hopefully that feels good. Why don't you guys try these two? Okay, here we have absolute value. Here we have the square root function. I want you to go ahead and try these, and then make sure you do it in pencil. And if you mess up, no big deal, we can change it. So go ahead and hit pause on the video, give those a try, and when you're ready, hit play. Alrighty, so let's see how we did here. Here my parent graph. I guess I should have stayed in blue, huh? My parent graph is the absolute value of x. Okay, so if I were to draw that graph, it would be 0, 0, 1, 1, 2, 2, right? And so on and so forth. And then also in the negative direction as well. But that's great and all, but what I'm really interested in is right here. This tells me that I go left 3, and then the minus 2 tells me I go down 2. Hopefully this is looking familiar since we did do it in algebra 2 as well. So I'm going to go left 3, 1, 2, 3, down 2. And then from there, you know what the graph looks like, right? Just up 1 over 1 over time. And then same thing here. There's my graph. Okay, last one here. My parent function is square root of x. So again, because I passed algebra 2, I should know square root of x goes 0, 0, 1, 1, 4, 2, and so on. So those are the 3 parent graph points, and we might even get time for another one, right? The next one is 9, 3. So we'll see how that goes. So if I'm going to be moving these around, this tells me I go left 4 and up 1. So this point, I'm going to 1, 2, 3, 4, up 1. And then 1, 2, 3, 4, up 1. 1, 2, 3, 4, up 1. Now, I do know that 9, 3 is a point. So if I'm at 9 and I go left 4, I go 8, 7, 6, 5. 1, 2, 3. But then I also have to go up 1. Oh boy, sorry. There we go. Notice I don't have arrows coming down here because my graph stops here at 0, 0, so it can't go any lower than this point. All right, so moving on to our next objective, we're looking at reflecting graphs. So it says compare 4 of the parent functions with transformations of these functions. What do you notice? So let's just look at the first one and the second one, I guess, but because I can't fit any more on my screen, right? I can only do 2. But it'll end up being the same idea no matter what. Okay, so here's my parent function. X squared, we know it's a parabola, we know what that looks like. Here is the graph of x squared with a negative in front of it, so negative x squared, where the squared is just applying to the negative, or to the x, and then the negative is out front. And notice what it does, so it's reflecting it, and now it's opening down. Okay, and then h of x is negative x squared, so now you're replacing your x with negative x, and it doesn't really look like anything has changed here. Okay, let's look at absolute value. Very similar when you have a negative outside the absolute value. Okay, it's going to reflect this over the x-axis. And again, when I have negative x inside the absolute value, it doesn't really look like anything happens. Let's look at square root. Okay, if the x is out or the negative is outside the square root, again, it flips it over the x-axis. But if the x is inside the square root, it flips it over the y-axis. So that actually might be a good tell for us, right? So that's a potential. And then the last one is x cubed. Negative x cubed is clearly flipped over the x-axis. And then negative x cubed, again, it's hard to tell. So we're going to make a little note here at the bottom of the page. What happens when the negative is outside the function? Okay, so if the negative's outside the function, this is reflected across the x-axis. If I'm replacing x with negative x, then it's reflected across the y-axis. Excuse me, it's been a long day. So here we can see that the h of x has been reflected over the y-axis for f of x. So if the negative is in front, you're reflecting over the x-axis. If the negative is inside the function, then you're reflecting it over the y-axis. So feeling good about that. We're going to do some practice. Okay, so I want you guys to try this one on your own. It says the graph of f of x equals x to the fourth. See there, is given in the first figure. So find the equation for A and find the equation for B. And when you are done, go ahead and hit play and you can check your work. So for A here, a couple things I'm noticing. First thing I'm noticing is that it is now opening downward, which tells me that my x to the fourth is going to be negative. So that's good to know. The other thing that I notice is that I did not move left or right. So that tells me that my x to the fourth is just going to be negative x to the fourth. Okay. And then the last thing is it has been moved up 2 units. So now the vertex is on the 2. So this is just plus 2. For B, let's look. Not only is it flipping downward, but it's also been moved to the right. So since it's flipping downward, I have a negative. And then since it's moved to the right, I have an x, minus 3 to the fourth. The reason it's a minus 3 is because we went to the right. And then this has not been moved up or down, so I'm done. I want you to try example 4 as well. So go ahead and hit pause on the video and try example 4. Find what the parent function is, find what has happened to the function, and then see if you can write the equation. And I will see you in a second. All right, so looking at this, the first thing hopefully I see is that my parent graph is the square root of x, which normally is like this. Okay, so a couple things that have happened here. I see that there's been an x-axis reflection. That tells me that it's going to be negative. I also see that it's gone left 2 units, right? It's supposed to be at 0, 0, but it's gone to the left 2. And I don't see anything else going on here, so I think I'm set to go ahead and write my equation. The x-axis reflection tells me that I have a negative in front of the square root. The left 2 tells me that inside the square root, I'm going to be x plus 2. And that's it. No big deal, right? No big deal. All right, same thing here for A, B, and C. I'm going to scroll down here. Graph the following without using a graphing calculator, using parent functions and transformations. So I want you to try these, and I'm going to put the answers up. And so when you're ready, go ahead and check your work. All right, so check your work here. Make sure that everything's looking good. If you have to pause the video, go ahead. My parent graph for A was x squared, and then I had an x-axis reflection, and I went left 2. So that's how I got these points. Same thing for B, right? I had an x-axis, or my parent graph, excuse me, is x, the absolute value of x. Make that better. And then I have an x-axis reflection, and then it moves up 3. And then lastly, for C, my parent graph is x cubed. Wow, words, that's not right. The square root of x is my parent graph. And we have to remember these are the points for the square root of x, right? So then I do a y-axis reflection. Well, this one stays there, and then down 2. So that's how I got this point. Here on a y-axis reflection, it comes over to negative 1, 1, and then down 2. And then here, a y-axis reflection goes to negative 4, 2, and down 2 gives me this point. So that's how we're getting those graphs there. So we're going to add on now. Now we're going to add what happens if the graph becomes wider or more narrow. Okay, what do I do then? So we're kind of getting close, okay? So the last, not the last thing, but the next thing that we're going to look at is non-rigid transformations. So rigid transformations means that the shape doesn't change. It just moves right, left, right, or up, down. Okay, but the shape stays exactly the same. Left, right, up, down. Non-rigid transformation now allows our parabola to become wider or more narrow, depending on the problem. So that's why this is a non-rigid transformation. It changes the shape of the original graph, and we look at it in terms of stretches and compression. Okay, so if the number in front of my function is greater than 1, say that again. If the number in front of the function, I should say that, well, yeah, if the number in front of the function is greater than 1, what's going to happen is I have a vertical stretch. So this is vertically stretched by a factor of 3. Okay, so what we mean by that is, let's say that I have a parabola, right? If I take the ends, the top of my parabola, and I stretch it vertically, so I pull it, right? I take it and I pull it vertically, that parabola is going to get more narrow because I'm pulling at it vertically. Okay, so a vertical stretch is going to make the parabola more narrow. If the number in front of my function is between 1 and 0, so any sort of fraction between 1 and 0, so in this case 1/3, it's going to be vertically compressed. So vertically compressed by a factor of 1/3. Okay, so same thing here. If I have my parabola and I vertically compress it, that means from the top and the bottom, I'm going to push down on it. Push, 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 push. So if I have this parabola and it's being pushed on, the parabola is going to go wider, wider, wider. Okay, so this makes it more wide, like out here, And then part A, if it's greater than 1, makes it more narrow. So I want you guys to try these extra examples. I'm going to clear them. All I want to know is it vertically stretched? Is it vertically compressed? What is there anything else happening in the graph? And what is the factor that it's stretched or compressed? So go ahead, hit pause, and then we'll talk about it. Okie dokie. So because my number here in front of the function in front of x squared is 2, this is a vertical stretch by a factor of 2. And we're going to talk in the next part about what that means, okay? Then for D, for h of x, because I have 1/2, this is going to be a vertical compression by a factor of 1/2. And then is there anything else going on in this problem? And hopefully we saw that that 1/2 is also a negative, right? So what does that mean? That means that and it's reflected over the x-axis. So not only does this have a vertical compression by a factor 1/2, but it's also reflected across the x-axis. Okay, so what we're going to do now is we're going to use this information to help us graph. I know I'm cruising, but you can always go back and rewatch it if you need to. Okay, so let's look at, okay, what does that mean for this? Since it has a vertical stretch of 2, all we do is we multiply each y coordinate, there we go, by 2. So we're just going to multiply all the y coordinates by 2. And the function is x cubed, right? So remember that the original x cubed function does this. And then it connects. Right, so it goes through -1, 1, 0, 1, 1. Since I have a scale factor of 2, that means that each y coordinate is going to get multiplied by 2. So here at -1, my y coordinate is -1. Well, -1 divided by, or times 2 is 2. So this is actually the point I'm looking at. Here at 0, my x coordinate is 0, but then my y coordinate is also 0. If I multiply 0 by 2, I still just get 0, so that just stays. And then lastly, I have 1, 1. Well, the y coordinate is 1, and I'm going to multiply the y coordinate by 2. So then it becomes 2. Just like that. Do you see how it's more narrow, right? It's being vertically stretched. Let's look at f, or f, this is the f, sorry, it's problem B. Okay, 1/3 x cubed, or square root of x. Why do I keep saying x cubed? So, square root, I have 0, 0, 1, 1, 4, 2 are my main points there. Just so we know what's going on. And I'm going to multiply every single y coordinate by 1/2. So multiply the y coordinate by 1/2. 1/3, not 1/2. 1/3. I'm real tired, y'all. Okay, so here my y-coordinate is 0. Well, 0 times 1/3 is just 0, so that stays. Okay. Here my y-coordinate is 1. Well, 1 times 1/3 is 1/3, so it's actually like down here. And then the next point is 4, 2, so the y-coordinate is 2, and 2 times 1/3 is 2/3, which is there. So I actually end up getting this compressed form of square root of x, right? It was a little bit more wide and tall, but because I vertically compressed it with this 1/2, it's more flat. Okay, and then the last one is, again, square root of x. So I'm going to go ahead and draw my parent graph. And notice I'm not connecting the points. I'm just drawing the points. Okay, so not only do I have a scale factor of 2, but it's also negative. So not only am I going to multiply my y-coordinate by 2, I'm also going to reflect it over the x-axis. So here my y-coordinate is 0, right? 0 times 2 is 0, and then reflected over the x-axis, it's still here. All right, here we go. 1, 1. My y-coordinate is 1. 1 times 2 is 2, but then I also have to reflect it over the x-axis. So here it is, right here. And then last, but certainly not least, I have 4, 2, right? So if I multiply that by 2, I get 4, 4. And then reflect it over the x-axis, I get negative 4, or 4, negative 4, excuse me. And there's my graph. Isn't it just beautiful? Again, make sure that you are reaching out if you do not understand something. Okay. Let's keep moving here then. Okay, so moving on to example 6. I want to graph h of x and f of x. Yes, sorry, f of x and h of x at the same time. I just got real tripped up by that for some reason. So f of x is given to me, it's right here. It's 2 minus x cubed. So I feel pretty confident to be able to graph this, right? This guy tells me that I go up 2, and then because this is negative, it's an x-axis reflection. Reflection. Okay, so let's go ahead and just do that one first. So again, x cubed starts at negative 1, 1. If I reflect it over the x-axis, it becomes negative 1, 1. Sorry, it wasn't negative 1, negative 1. Now it's negative 1, 1. And then I go up 2. So negative 1, 3. Next point normally would be 0, 0. Well, if I reflect that, it's still 0, 0, and then up 2. And then the next point would have been 1, 1, but when I reflect it, it becomes 1, negative 1, and then I go up 2. Actually, back to the original point that it was already on, but that's okay. And then I can draw my line. So there's the first one. Okay, let's find a different color for the second one. Now, h of x says h of x is the same thing as, hey, I'm going to plug 1/2 x in for f. So here's f, right? Instead of x, it's going to be 1/2 x. So I have 2 minus 1/2 x squared. So all I did was instead of, sorry, it's a cubed. All I did was instead of x cubed, it's 1/2 x cubed. So here, I know that this is up 2, so that makes me feel good, right? I know what that one is. Now, this one is a little bit tricky because do you see how the 1/2 is inside the function, right? It's not 1/2 out here and then x cubed. So this is going to be really important. When you have that interior number, it's a horizontal stretch or compression. So this is a horizontal compression slash stretch. So it depends on what the problem is, right? Sometimes it could be a compression, sometimes it could be a stretch. Okay? Now, this is where it gets tricky. By a factor, we would think it would be 1/2, right? But it's not. It's the reciprocal of 1/2, which is 2. Okay, so whatever this number is in front of your x that's inside the function, you're just going to take the reciprocal of that, and that is what you're multiplying by. So this tells me to multiply now the x coordinate by 2. So we're going to go ahead and try this here, okay? So again, my normal point would be 0, 0. The x coordinate of 0, 0 is 0. So 0 times 2 is still 0. And then I just go up 2. So that shares a point, but that's okay. Let's look at 1, 1, 1, 1. What am I doing? Oh, the x coordinate of 1, 1 is 1. 1 times 2 is 2. So it's going to be out here. So hopefully that makes sense. Boop. Oh, I forgot to move it up 2. Oh, and it has an x-axis reflection. You guys, why are you not yelling at me about this stuff? Holy moly. Okay, let's try this again. So it's negative. Okay, so 1, 1. It's then comes out to 2, 1 because of the 1/2. Then it reflects over the x-axis because of the negative, and then it goes up 2. Whoosh! That's a lot. Last point here is -1, -1, right? The x coordinate is -1, so if I multiply that by 2, sorry, here, if I multiply that by 2, I get -2. Then I have an x-axis reflection up to -2, +1, and then I go up 2. And I'm going to try real hard to make this look good. Close enough. Okay, so this red one is h of x. And then the blue one is f of x. Just so we can keep them straight. All right, my friends, we are getting real close here to being done. The next, well, let's do 1 together, and then I want you guys to just really try it. Okay, we're going to do 1 together, we're going to do a together, and then I just want you to try some of these, okay? No big deal. All right, first thing you have to be able to do is recognize your parent graph. In this case, my parent graph is x squared. If it helps you to put the original points of the parent graph, then you are more than welcome to do that. If that doesn't help you, then obviously don't do it, okay? Okay, so here here I'm told it goes up 4, right? The -3 is inside the parentheses, so that's to the right 3. And then this tells me that I'm multiplying the y coordinate by 2, and I'm reflecting over the x-axis. So let's start here. The y coordinate is 0. 0 times 2 is 0. Reflected over the x-axis is still 0. And then I go right 3, up 1, 2, 3, 4. There we go. Now here we go here. 1, 1. The y coordinate of 1, 1 is 2, so I have 1, 2. Then I'm going to reflect it over the x-axis. Then I go right 3, up 1, 2, 3, 4. And because parabolas are symmetrical, I can just go ahead and draw it on the other side too. I don't have to actually calculate it. All right, and then the last one is 2, 4. The y-coordinate of that is 8, is 4. So when I multiply it by 2, I get 8. So then when I reflect it, I'm down here at -8. And I go up 4, so 7, 6, 5, 4. And then over 1, 2, 3. And again, parabolas are symmetrical, so whatever you do to one side, you can just automatically do to the other, and that's kind of nice. Okay, I want you to try B, C, D, E, and F, and then we'll go through the answers one at a time. So go ahead and hit pause. I'm going to put the answer up for B, and then so when you're ready, hit play. All right, so let's look at B here. We're looking at absolute value. Okay, so a normal point for me for absolute value would be at 0, 0, right? Then I'm moving, or I multiply the y-coordinate by 1/2, so it's still 0, 0. Reflect it, so it's still 0, 0. And then I go left 3, up 4. So that's how I got this point. Then the next point for me would be 1, 1. If I multiply the y-coordinate by 1/2, I get 1, 1/2. Then I reflect it, so I get 1, -1/2. And then I move left 3, up 1, 2, 3, 4. So it's kind of right in the middle there. And then we keep going, right? 2, 2. If I multiply the y-coordinate, which is 2, by 1/2, I get 1. Then I reflect it. Then I go left 3, up 1, 2, 3, 4. Okay, so hopefully we feel good on that. Before I let you go on the next one, I do want to talk about this negative that's in here. It's kind of tricky to know which way you actually go. Do you move it left or do you move it right? Because this negative is here. So if you ever don't know, just set whatever's in the parentheses or bracket or whatever it is equal to 0 and solve. So negative x equals 3. So x equals -3. So this tells me that this is actually moving left, even though this is a negative. Okay, so go ahead and do C, and I'll see you in a second. Okay, check your work here for part C. The only thing here that was actually really tricky was just figuring out which direction this 3 was going. Because this negative was here, we actually solved for it. So you should have gotten a graph that looks like this. Move on to D, and I'll see you in a second. All right, here's our work for D. My parent graph is x cubed. And the only thing that's really happening here, so like at -1, -1, is I'm reflecting over the x-axis and then going left 4, up 2. Okay, so same thing, 0, 0, I reflect it, then I go left 4, up 2. Next point would be 1, 1, I reflect it, then left 4, up 2. And that's it. Go ahead and give E a shot, and we'll see you soon. All right, so E was a little bit tricky here. This is what it should look like. And the only thing, if yours is going the other direction, the only thing I want to point out here is that you have a y-axis reflection as well. We didn't talk about that in part C just because it was a parabola, and so it didn't matter that there was a y-axis reflection. But I have an x-axis reflection because of this negative, and then a y-axis reflection, excuse me, because of this negative. So actually, this is the graph that we're looking at, right? So 0, 0. If I reflect and then reflect again, nothing happens, and then I go left 5, up 3. Then 1, 1. If I reflect over the y-axis, and then again the x-axis, and then left 5, up 3. Okay, one last one for us to try. So put in some effort here, and then you can check your work soon. All right, so last one to review here. Sorry, my graph got a little messy, okay? I have a y-axis reflection because of this negative x, and I'm multiplying the y-coordinates by 3 and moving down 6. So a parent graph point here is 0, 0. So if I reflect it, it's still 0, 0. Multiplied by 3, still 0, 0. And then I go down 6. So that's how I got this point here. The next point is 1, 1. So if I multiply it, the y-coordinate by 3, I get 1, 3. Then I can reflect it over the y-axis, and then I go down 6, which is how I got this point. And the last one I can fit is 4, 2. If I multiply this by 3, I get 4, 6, right? And then if I reflect it over the y-axis, I get negative 4, 6. And then when I go down 6, I get negative 4, 0. And I can connect it. Hopefully we're good. A lot of this should be reviewed from Algebra 2, so hopefully we're at least like recognizing it, even if we don't remember how to do it, but at least like, okay, I acknowledge that I have seen this before. Okay, and then this is almost the last problem. We're almost done. I know that this is a really long one, so hopefully you've been breaking it up into smaller pieces here. It says identify the parent function. Okay, write an equation for the graphed function. So looking at this, just the general shape of it, I feel pretty confident in saying that the parent function here is the square root of x. Okay. So now I just need to start writing down some observations from the parent graph to this graph. So the first thing I notice is that there has been an x-axis reflection, right? The graph is now going down. I also know that my original starting point for the square root of x is at 0, 0. So I can tell that this has been moved to the left 1 unit. I can also tell that it's been moved down 2 units. Okay, now I need to try to figure out if there's a vertical stretch or not. So normally from 0, 0, right, the next point would be 1, 1, which is here. But instead, it's over 1, down 2. So that tells me that there's a vertical stretch of 2. Okay, so that tells me there's a vertical stretch of 2. And once I know all that information, I can write my equation, right? So f of x is equal to, since there's an x-axis reflection, it's a negative, square root x. And then I went left 1, so this is going to be plus 1 because I went to the left. And then down 2. Oh, and I forgot my vertical stretch of 2, so that should be a negative 2. And that's it. There's my equation. So f of x equals negative 2 times the square root of x plus 1 minus 2. Make sure that this minus 2 is outside the square root, because otherwise it'll be a horizontal shift. But you really want it to be a vertical shift. All right, we are on the last page. We are so close. Give yourself a pat on the back, okay? This is extra practice. And so what I'm going to do is I'm going to do these first two with you, and then for the C, D, E, and F, I'm just going to review with you the answers. So you'll pause the video and try it yourself, okay? So what we have going on here is it says use the graph of g of x to sketch each graph. So here, this graph, this original graph, is g of x. The problem tells me that I'm doing something, right? In this case, I have g of x, which is this equation, plus 2. Well, since this plus 2 is outside of the function, this just tells me that I go up 2. So I'm just going to like estimate, right? So then every single point I have is going to move up 2. And then we just draw, oops, and just draw it. And that's it. Here, again, I have the graph of g of x. The only difference is I have this negative. Well, that negative tells me that I need an x-axis reflection. So I'm going to take each point and I'm going to reflect it over the x-axis. And then I'm going to connect them. Boom, that's it. Okay, so we're on the home stretch here. So go ahead and do C and D. And then when you're done, let's check your work. All right, so check your work here. For C, this is just telling me I'm just moving everything 3 units to the right. Okay, so I just moved every single point 3 units to the right. Not very beautifully, but I did it, right? And then D, because this negative is inside the function, that's going to be a y-axis reflection. So I reflected every single point over the y-axis. 2 more and we're done. So let's clear these out. Scroll down. What we're going to do, again here, multiply the y-coordinate. Here you multiply the x-coordinate by the reciprocal. So I'm going to make a note of that, okay? So we're going to multiply the x-coordinate by the reciprocal. Whoops. All right. There we go. Of the value in the function. Okay, so using that hint right there, go ahead and try these two, and when you're done, hit play. Okay, so last 2 here. For E, you want to multiply the y-coordinate by 1/2. So here the y-coordinate is 3, so I just cut it in half to 1.5. Here the y-coordinate's 3, cut it in half to 1.5. Here the y-coordinate's -1, cut it in half to -0.5. And then here the y-coordinate is 8, so we cut it in half to 4. And we get something that looks like this. And then with F, you're going to multiply the x-coordinate by the reciprocal. So the reciprocal of 1/2, or of 2, is 1/2. So we're actually going to multiply the x-coordinate, and I'm going to abbreviate, by the reciprocal of 2, which is 1/2. Okay, so here my x-coordinate is -3. If I divide that by 2, it's -1.5. Here my x-coordinate was 2, so if I divide that by 2, it's 1. And then here my x-coordinate was 5. If I divide that in 2, it's 2.5. And then I connect it. All right, guys, nice job. I know that this was a longer lesson, and there's a lot of information going on in here. If you have any questions, if you need anything, please reach out to me. I'm always available to you. Email, remind, whatever you need, just let me know. Otherwise, I will see you guys soon, and have a great day.